Grade 12s, we're on our second day of trigonometry and we're going to look at some special angles. I think it would be most helpful for you if you had the sheet BLM 1-3 in front of you and you can kind of fill out some of these answers as we go. We're going to use that sheet to help us with a few lessons and to cheat from it on the test. So it would be good to have that in front of you. Otherwise, I'll produce a copy for you for tomorrow. I want to talk about certain angles that we see often, and we would like to display our answers for these particular angles as exact fractions that may include square roots but not a decimal equivalent. We're going to leave them as perfect ratios and use those whenever we solve a problem with these nice angles. The first angle we want to look at is 30 degrees. So I have some playing to do first. The large triangle you see in front of you has all equal sides of 2. So it's an equilateral triangle. And you know in an equilateral triangle, all of the sides are the same. And all of the angles are 60 degrees. What I would like to do is actually cut that triangle in half and just look at the half triangle that's in dark. So that has a length of 1 because I've cut it in half. There's a right angle in there because with an equilateral triangle, if you drop a height along there, it would meet the base at right angles. So I know 2 of the lengths of my dark triangle on the top are 1 and the hypotenuse would be 2. To find the length of the bottom of my dark triangle, I'm going to use Pythagorean theorem. So for Pythagorean theorem, c squared equals a squared plus b squared. My hypotenuse for that triangle is a 2. The other two sides, the order doesn't matter, so I've got 1 squared plus x squared. And I want to get x by itself. So I have 2 squared, 4. I'm having such a time with this machine again. 4 equals 1 plus x squared. I'm going to subtract 1 from both sides. So 3 is x squared. We know that we want the length of the bottom, so I don't need to consider the negative, but I'm going to take the square root of both sides. X is root 3. So my triangle has lengths of 1, 2, and root 3. I know that the formerly large triangle had angles of 60 degrees in every corner, so this angle is 60 degrees. Since I've cut the large triangle in half to just consider the top half, this angle will be 30 degrees. So I have all of the data that I need for that top triangle to write my ratios. Sine of 30 degrees. Since it's the 30-degree angle that we're thinking about on this slide, I'm going to label my triangle with opposite, adjacent, and hypotenuse, and it's always a good habit to be in. Longest side is hypotenuse. The one furthest away from the angle of reference is opposite, and adjacent is the one that's left over. So sine, let's write our memory device down here, so katoa. Sine of 30 degrees is opposite over hypotenuse, which is 1 over 2. So on your chart, BLM 1-3, for 30 degrees, write sine under sine theta, write 1 over 2. Cos of 30 degrees is adjacent over hypotenuse, which would be root 3 over 2. And tangent of 30 degrees, opposite over adjacent, would be 1 over root 3. We see 30 degrees a lot. Those three ratios we will leave as fractions with radicals in them so that we have exact answers. 60 degrees. We're going to consider that angle and we're going to look at the very same setup as the last one. I have an equilateral triangle that I have divided in half. Any equilateral triangle will have equal sides. I've chosen to make them all 2 so that when I look at half of that triangle, I have a length of 1, a length of 2, and a length of root 3. This was 60 degrees because it was an equilateral triangle to start with. Half of it is 30. We have the same setup as last time, but this time we are going to look at 60 degrees as our angle of reference. So I can have the 3 ratios for 60 degrees. For the 60-degree angle, this is still the hypotenuse side, but the root 3 is opposite. adjacent is 1. So sine of 60 degrees is opposite over hypotenuse, which would be root 3 over 2. Cos of 60 degrees is adjacent over hypotenuse, which would be 1 over 2. And tan of 60 degrees is opposite over adjacent, which is root 3 over 1. You can write it over 1 or just write it as root 3. You should fill those 3 out on your chart as well. One that I want to finish with is 45 degrees. We know that shows up often. I've tried to draw a right angled triangle that is an isosceles triangle that has equal sides. So just to determine our ratios, I am going to make my triangle with equal sides of length 1. So if I had this triangle and I wanted to find out the length of the hypotenuse, I would have to use Pythagorean theorem again. A squared plus b squared equals c squared, where both the shorter sides are 1, and I am trying to determine the longer side. I would set it up like that. 1 squared is 1, and 1 is c squared. C squared is equal to 2. I'm looking for a length, so I'm going to take the positive square root of both sides. C is the square root of 2, which is not a pretty decimal, so I'm going to leave it like that because it's so exact. Root 2. Now, both of these corners, because it's an isosceles triangle, 45 and 45. So I can choose either one that I want as my angle of reference. I like the look of this guy better. So if that's my angle of reference, I'm going to label my sides: hypotenuse, opposite, and adjacent. The hypotenuse is the easiest one to start with, the longest. Opposite is across the triangle, is 1, and coincidentally the adjacent is also 1. So the sine of 45 degrees, whoops, equals opposite over hypotenuse is 1 over root 2. Cos of 45 degrees is adjacent over hypotenuse, which is 1 over root 2. And the tan of 45 degrees is opposite over adjacent, 1 over 1, or 1. Can you make sure that you have filled those in on your chart? I'm going to fill up to 90 degrees, and then in your textbook, pages 2, 1 to 3, 8 to 10.